Can't see the team side of it, so I'll assume that it popped up and that we are recording. Hi, everyone. My name is Sydney Jones, and I work for Ecosystem Planning and Restoration. And I'm going to take you through the workbooks, the actual tools that we developed. So the stream quantification tool, and then there is a second workbook, the debit calculator, that were developed for the Alaskan interior. So first, we're going to start with a purpose, and I know we started the day with Matt kind of saying like why it was needed and how it can really be used as a communication tool between the different agencies that are all talking about stream functions. And from our perspective, the purpose of the SQT is really we developed all of them to determine numerical differences between an existing stream condition and a proposed stream condition. And to specifically link in-channel activities. So in this case, we're talking about restoration, but also impact activities, but just reach scale activities to changes in stream functions. And that will link restoration goals to restoration potential. And I'll talk about that a little bit. And I know Will kind of, he couldn't leave the first presentation without, talking about restoration potential, because that is such a big goal of where this all started with the stream function pyramid framework, with this tying into number 4 on this list, which is incentivizing high quality stream mitigation. So really recognizing what is possible for your particular stream reach and monitoring and measuring and thinking about all 5 functional categories of the stream functions pyramid. And lastly, a purpose of the SQT is it can assist with site selection. So finding the site that can meet the needs of your particular project, and if that would be, maximizing the lift, or if you have a specific species goals that you're trying to accomplish, then the SQT can help you kind of priority rank different projects if you're considering multiple options. I love this slide. It shows kind of how the SQT is sitting in between multiple drivers. So the SQT isn't a whole condition assessment of stream functions. Like we used function-based parameters, and really the parameters and metrics that get selected are those that are thought to be sensitive to reach scale activities. So there's a whole lot of stream functions that are very important, but they may sit outside the SQT, or maybe we capture them more in the catchment assessment so that we can frame it in terms of restoration potential for that particular reach. And then the SQT in some states is very specifically developed for compensatory mitigation under 404. But there are, I know Will was talking a lot about like reclamation, and just there are multiple regulatory programs that assess and evaluate stream function. So kind of the SQT sitting in the middle of those 3 drivers. So this particular SQT was developed for the Alaskan interior. And if you can see kind of the red outline on the map there, those are the ecoregions that we consider part of the Alaskan interior. It was developed primarily with data from single thread channels. They are weightable and non-glacial valleys. So colluvial, alluvial valleys, not the highly dynamic systems that are in the glacial valleys. The framework that Will presented, so the idea of, functional categories, parameters, and metrics are applicable to other systems. So thinking about intermittent, ephemeral, or even non-weightable streams, it's just that the data that is in this SQT for the reference curves was developed primarily from single thread weightable non-glacial valleys. As Will noted at the beginning, when he had the slide, I love the slide that has like, the engineers, geologists, geomorphologists, and ecologists on the side, because we all have our own perspectives. And that means we all have different skills as well. And it really does take a multidisciplinary team when we are looking at all 5 functional categories and evaluating the impacts of reach scale activities on all 5 of those functional categories. So you need geomorphologists, and you need plant biologists, ecologists, hydrologists, engineers. Like it takes more than one skill set to really look at the stream from a more whole picture, more holistic view. I am going to talk about 2 workbooks today, but I'm going to spend the bulk of my time talking about the SQT Excel workbook, which is for just one reach, and I'll get into reach delineation in a couple slides. The SQT workbook contains 7 worksheets. I will, at the very end, talk about the debit calculator and how it is an application of the SQT for one specific purpose. That workbook has 5 worksheets, and it can hold up to 10 reaches instead of just one. And I'm not going to get into the worksheet today, but following my presentations, Will's going to take you through a case study where you will actually get to see him navigate throughout and enter data into all the different worksheets and how they talk together. What I'm going to focus on more today is the SQT process that we follow. So this is actually figure 13 from your user manual, and it takes you through the 6 steps to kind of follow for the SQT. Step 1 is identify project area and delineate the reaches. Step 2 is complete the project and catchment assessment worksheets. Step 3 is identify basic site information. Step 4, select parameters and metrics to evaluate. Step 5, collect field and desktop data. And step 6, enter field data into the SQT or debit calculator. So starting with that step 1 of identifying the project area and delineating reaches, it's important to note that the SQT, as an assessment, you want to break your project into distinct reaches that have similar characteristics for all the parameters that you are evaluating. So think of like reach breaks you're going to have. If you have a main stem and a tributary, then those are separate reaches. But if your main stem has a significant slope break in it, then you'll have a separate reach for the steeper portion than for the flatter portion of the reach, because those have 2 distinctly different conditions that you're going to measure and evaluate. So reach delineation is primarily landscape driven and potentially restoration approach driven as well, just based on like, if this reach is going to be more enhancement, this reach needs a lot more work, its condition has significantly changed. If you do have a particularly long reach in your project area, there is what we call a subreach. It's a representative subreach assessment that you can use to assess some of the metrics that are in the SQT. So when Will was showing you guys pool spacing and percent riffle, if you have a 5-mile long reach that is pretty, consistent conditions, you do not need to, go find every single pool on that 5-mile long reach. You can do a representative subreach to collect your quantitative data and collect it there, and that'll represent the whole reach. This slide is to stress that the SQT is a reach corridor assessment, and you probably gathered this from Will's presentation because he started at hydrology, and how we characterize the hydrology for each reach is by looking at the water that is coming in from adjacent land uses, so that lateral drainage area. So, well, a lot of the data is collected from the actual inside the channel. We also look at land uses draining to it. We look at the floodplain width, and we characterize the riparian vegetation that's in the valley of the stream. So it is a reach corridor assessment rather than just a within the banks, kind of like limited by the ordinary high water mark. All right, on to step 2 of that SQT process. So step 2 is complete the project and catchment assessment worksheets. So once you've taken your project area, evaluated the condition, broken it into different reaches, determined where you're going to collect your different data, if you have a representative subreach, you're going to perform what is kind of the restoration potential process. So this flow chart here is showing you the end goal is kind of just determining that restoration potential. So whether or not you can restore biology to a reference condition, to fully functioning biology, that would be a full restoration potential, or whether or not your focus is going to be more on providing stability and habitat. Not that you can't have physicochemical or biological lift in that scenario, you're just admitting that the stressors of the watershed or the conditions are such that you can't restore biology to a fully functioning condition. And that would be a partial restoration potential. And this step starts with the catchment assessment. And then I'll skip to this part because this is, We don't get to spend enough time on this and how important it is. But as you work through the restoration potential process, you are identifying your reach specific goals and objectives for that reach. What can you do here and how can you provide lift? And how does that, relate to what is the existing condition in addition to what was the historic condition? So the reference stream type. This is important. I'll come back to it much later in my presentation. But step 2, complete the project and catchment assessment worksheets. The project assessment worksheet does require you to list the goals and objectives for every specific reach. All right, so step 3, identify basic site information. So on the quantification tool worksheet, right at the top in the upper left-hand corner, the first thing you will see is the site information and reference selection section. And you can see that it contains mostly basic site information. So your project name, restoration potential, reach ID, existing and proposed stream length, stream types, valley type, drainage area. All very important information, information you probably have for all of the sites that you are considering. Some of this information is used to stratify reference curves in the SQT. So I'll tell you right now, if you enter a field value for a metric and you don't get a score, or if it tells you false in your index value when you're expecting it to give you a number, or it gives you a number you weren't expecting, it's due to either missing information or incorrect information in this section, the site information and reference selection section of the worksheet. So the ones I have highlighted here, reference stream type, valley type, bed material, slope, ecoregion, and fish assemblage, are used to choose the correct reference curve for different metrics in the SQT. In the science document, there's an appendix that summarizes all of the reference curves and all the stratification. And hopefully today I'll have time to show you guys that appendix. But just know that that information is there in one spot. You can go look up, whether a metric has stratified reference curves and how it's stratified. I've used the term reference curve, and I know Will introduced the topic with the promise that I was going to go into a little bit more detail. All of the reference curves that we developed and used as part of regionalization are in the reference curve spreadsheet. So there's no input on that spreadsheet in the quantification tool. They're simply there for you to see them and reference them so that you can see what we did and how it's calculating the numbers. Some reference curves, as I noted before, are stratified by different either stream type, ecoregion, reference community. So not all metrics have a stratifier, but if they do, you need to choose the correct stratifier in the site information section of the spreadsheet. I'm going to come back to, I think Will showed each one of these pictures as kind of examples of like the quality and the bins that we put in. So in the SQT, those reference curves, the y-axis is always the same scale of 0 to 1. And we're putting the scores into these 3 categorical bins of not functioning, functioning at risk, and functioning, where 1 is this pristine condition, the best that we could find in an unaltered watershed for that particular region. 0.7 is the minimally altered, still functioning, still supporting a functioning ecology. Oh, what's the Stoddard reference? Biological integrity. There we go. Supporting, for biological integrity of that stream. And then the 0 to 0.3 is this not functioning bin where it's really not supporting biological integrity for that stream. So going back to the reference curve that I showed, this particular one is for vegetative complexity. You can see that vegetative complexity is stratified by ecoregion. So here I'm showing the interior bottomlands and the interior forested lowlands and uplands. And here I've added kind of a color shading on top to show, so that 0.7 to 1 range on the y-axis is what we consider functioning. So the x-axis of every single reference curve is always that value that you measure, calculate, and enter into the SQT. And the y-axis is that 0 to 1 condition score for that particular metric, for that particular stratification. And on every reference curve, we show the calculations, the linear interpolations that we use to calculate the index value from the value that you provide as the user on that x-axis. How do we develop the reference curves? Well, we have an entire manual that tells you exactly how we did it. Please look at it. We spent a lot of time writing it. It's wonderful. It is the science document. It's available on Ribbits. I will send it to you. It's great. You should read it. Here's kind of the one slide version of how we developed them. So where we have it, we used existing data sets. So the metrics that are from the BLM AIM assessment, we did use that data that they collected throughout the interior to set those thresholds. So they had reference sites and they had degraded sites. And we set our thresholds for those functional capacities using the data. For some, like impervious cover, that is an assessment for, or sorry, a metric for reach runoff or catchment hydrology. There's peer-reviewed literature that shows, the detrimental impacts of impervious cover on receiving waters. And so we can set thresholds from available literature, government documents, just published papers, published documents. I think I said documents too many times. From there, especially for physicochemical, we're usually looking at existing indices from state water quality programs. So again, looking at like Alaska-specific data sets. And sometimes that goes hand in hand with kind of a best professional judgment. So as Matt pointed out, this was a collaborative effort between multiple agencies of people who work in and, measure or receive all the data of measuring turbidity in Alaska streams. So we worked with the Alaska DEC to talk about how to score those and how to not only measure them, but score them for reference curves. Appendix B of the science document, that is wonderful. You're all going to read it, documents everybody who was on those technical teams. So if you're curious, you can go refer to our best professional judgment list. Okay, coming back to my flow chart to keep me on track. We have covered the first 3 steps. The next 3 steps are where you're going to spend a lot more of your time, and I right now am going to spend the least amount of time. But I will say Will's presentation before lunch was a lot about collecting field data and some of that desktop data. So like land uses for the land use coefficient, like that's a desktop exercise. How do you actually go out in the field and measure a bank height ratio? That's field data that you collect. I am going to let's see, Will's going to cover a lot of entering data into the SQT when he goes over the case study. So I'm kind of going to stop at step 4, which is selecting parameters and metrics. There is in the SQT workbook a worksheet that helps you and provides guidance for when different parameters and metrics are applicable or used for your site. So as Will noted, he introduced all of the required parameters. If you go to that worksheet, you would see, large woody debris is only applicable where there's a natural supply of large woody debris. So if you're really like, in a scrub shrub system and everything upstream of you is scrub shrub, you don't have a supply of large woody debris and you wouldn't use that parameter or the associated metric. If you are in a reach that does not have armoring present or proposed, you would measure lateral migration as a parameter, but you would not use the armoring metric for that system. So all of that is summarized in the metric selection guide worksheet of the SQT. And I'm going to point out a couple specific rules about parameter and metric selection. So for the SQT to work, you have to assess the same parameters and metrics for the existing condition and every single condition assessment after that. So the existing, the proposed, the as-built, and all of the monitored conditions, you have to provide field values for the same metrics in every condition assessment. For metrics that are not selected, the metric is not included in the scoring. So if there's no armoring present or proposed, don't put a 0 in for both the existing and proposed condition. If it's not selected, it's not included in scoring. So this slide kind of is my segue slide to talk about scoring, because these metric selection rules that you cannot break when using the SQT are incredibly important when it comes to scoring. I will say the final two bullets on my slide are just important notes that you can't really compare sites between sites when you have different parameters or metrics selected. So if I'm in an ephemeral system and I haven't, like, I'm not using some of the same parameters or metrics because they're not applicable to that system, I will still get scores. I will still get SQT outputs, but it's not fair to compare that to, say, a perennial second order stream and the score that I would get from the SQT. If I haven't assessed the same parameters and metrics, it's not comparing apples to apples. And just a note that the core, you got to work with the core for your parameter and metric selection if you are using the SQT for compensatory mitigation. Okay, but why spend so much time talking about these rules? Like, it is important because of how the SQT does scoring. We use kind of a roll-up scoring method where things are averaged rather than weighted. And this keeps the SQT flexible. So as the science changes, as we develop better measurement methods or metrics or different parameters are identified as being important, we can add them in without, reevaluating all the different weightings that are contributing to the SQT. So this is a numerical example because my brain really likes numbers, and it also shows you some screenshots from the SQT. So if in my catchment, assessing catchment hydrology, if my catchment is 5% impervious and 60% anthropogenic land cover, then when I enter those field values in the SQT, I'm automatically going to get scored for the index values using the reference curves. My score for that parameter, catchment hydrology, is an average of those two metric index values. When I enter multiple parameters, or when I've assessed multiple parameters, my score for the functional category, in this case hydrology, is the average of all the parameters that are assessed. So again, it is incredibly important that you assess the same metrics for all condition assessments for a single reach. And just know that if you're not assessing metrics, then they are not included in the scoring. So, this catchment hydrology value is an average of these two numbers. There's not a zero or an implicit zero here for land use coefficient. If it's not assessed, it's just not accounted for in scoring. So here's more of a colorful depiction of what I just outlined, that you're going to enter a field value for each metric. Those are going to get scored as index values on that scale of 0 to 1 using our reference curves. For the parameter is going to be an average of the metric index values, and that's going to be the parameter score. The functional category score is the average of the parameter scores. And then for the overall reach score, every one of the 5 functional categories in the stream functions pyramid is weighted. So you have to assess all 5 functional categories to kind of be on that same scale of 0 to 1. So this says, like, for your overall reach score, you're going to multiply the functional category scores by 0.2, so 20% for each of the 5 functional categories, and add them up. So the SQT outputs 2 primary results, and I have lots of slides to follow this that stress this idea. There's 2 results that you're getting out. You're getting a change in condition. You're getting a proposed condition score and an existing condition score. And then the change in condition is the proposed minus the existing. So for impact projects, if the proposed condition is, worse off than the existing, this number is negative and can be used to help calculate debits. This is a change in condition, but it is also unitless. So if I'm installing a culvert that is only 20 feet long, I have a very large change in condition, but it's a very short reach. So the end output of the SQT is what we call functional feet. Linear feet is the unit of measure that is used in the SQT or in all SQTs. That is a regulatory decision. So we scale that condition score by stream length. So We calculate the existing functional feet by multiplying the existing stream length by the condition score. And then the proposed functional feet are calculated by multiplying the proposed stream length by the proposed condition score. So if you are adding length to the stream, you're going to have a kind of a multiplier, right? Like you are improving the stream that is there, and then you're also adding length, and you'll have a bigger delta. If you are shortening a stream, then you'll see kind of a bigger negative number, more negative number. It's still a larger delta for that condition when you change the length of the stream. Okay, so two outputs for the SQT, condition change and then a change in functional feet, which we call a delta lovingly. So a little bit more about output one. This is a nice visual representation that shows that kind of last step of the scoring of the SQT, where each one of these 5 functional categories is important. Even though I am an engineer and I primarily do H&H modeling, and I might be the engineer that will said at the beginning that my goal is to transport water. That's what it's got to do. It's a flood control channel. So I want to focus all my efforts down here. There are 5 functional categories and each one is equally weighted. So if your condition scores, in order for your condition scores to be out of 1, you have to assess all 5 functional categories. If you only assess 4 functional categories, the maximum score you can achieve is a 0.8. If you only assess 3 functional categories, then your maximum score is a 0.6. I have an example later, and when Will does his case study, just keep that in mind when you're looking at the condition scores that are output from it. When you only assess up through geomorphology, it's not really out of a 1 anymore. All right, so output 2 is that functional change. So again, that condition score, which is a % of functioning when you've assessed all 5 functional categories, multiplied by that unit of measure, which in this case is the length of the stream. And that equals your functional feet. And really, the output of the SQT is all about the delta, that change in conditions. So when your proposed is better than existing, that's a positive number yielding functional lift. When your proposed is worse than the existing, that's a negative number yielding functional loss. Couple slides just to drive home. Remember I think it was my first slide where I had the purposes of the SQT. We wanted a tool that did a numerical change. So in this particular example, I'm showing somewhat like a fairly well off stream for the existing condition. It's a 0.6 and it's going up to a 0.8. So in this case, you're turning all the numbers green. So when you get into the SQT and start entering numbers, you'll see that things are color coded, and green is good, green is functioning, and red is not functioning. So you're going to want to turn everything green. But just remember this slide and the next slide when you try to do that this change in conditions, so turning everything green, yielded 0.2 of lift. So you ended at a high quality, but you only had 0.2 of lift. Whereas if you have a, pretty terrible stream, not functioning near, bottom of the barrel kind of stream, but you have a lot of opportunity there and you can provide a lot more functional lift. So in this case, this is double the lift up at 0.4. You're only middle of the range functioning at risk when you end, but you've generated more lift. So remember that, the change in condition is really the credit or the debit. So the more change you have, well, in this case, if you're increasing it, the more change you have, the better. If you're impacting it, then, you want to minimize the change in condition. But keep in mind, even though the temptation is there to turn everything green, your goal is to maximize the change for restoration. So here's just some pictures to show what I've been babbling on about. So we have the existing condition on the left. This is an existing condition score of 0.19. It is only assessed through geomorphology. Your existing stream length is 972. So the functional feet are the product of those two numbers. And for the proposed condition, we've had increase in the proposed condition here. This is a picture from 5 years post-construction, so kind of at the end of the monitoring period. we've achieved a decent delta. We did increase the stream length. So the functional foot here, 448, is calculated by multiplying these two values, and then you calculate a delta by the proposed condition score minus the existing condition score. This is a positive number, so we did achieve lift. We achieved 263 functional feet of lift. So I can tell you how much better this picture on the right is compared to the picture on the left. And if you go into the SQT, you can actually see where the lift occurred by parameter and by functional category, like how was that lift achieved. These next two numbers, P2, tells me that this lift was achieved in a perennial second order stream. In the SQT, you will see that flag as just kind of a notification, because again, you can use this to assess a perennial first order stream, or you could use it to assess a perennial fifth order stream if it's still weightable. It might not be, or maybe an ephemeral first order stream. The SQT will provide a change in condition. But this flag is mostly there to just identify like what kind of stream it is associated with, so you can better match credits and debits. So if this is lift occurred in a perennial second order stream, you'd want to use that to offset impacts in, a similar perennial second order stream, preferably. Definitely, probably not a perennial fourth order stream, because those are just different resources. All right, some more screenshots from the SQT. So up at the top, right next to that site information and stratification section, you're going to see this functional change summary, which is laying out all the numbers that we were talking about. So the existing condition score, the proposed condition score, change in condition, all of the numbers you need to calculate the delta. And in this case, you'll see I have 289 functional feet of lift, and this one's a perennial third order stream. And we also added this yield, primarily for practitioners, where you're probably looking at project costs based on the proposed stream length. So this value, the proposed stream length. So this functional feet is this value, the delta, divided by the proposed stream length, so that it can help you kind of quantify how much yield your project will get, how to turn that into dollar values. This is my favorite summary output from the SQT. It is the function-based parameter summary, where you can see where lift occurred on all the, well, you can first see what parameters were assessed and what functional categories were assessed, and then also determine where lift occurred. And if you put this summary side by side with your goals and objectives, it should tell the same story. So if I'm doing something for bank stability, then I should see, an increase in that lateral migration score. If one of my goals is improving large wood and I didn't assess large wood as part of my assessment, then that should throw up a red flag, like one of my goals was to assess, to improve large wood. So I should be measuring that to show that I achieved that goal. There's also a summary table that shows lift and condition. Sorry, it shows the condition score lift, but also the change in functional feet for the functional categories right next to this summary table in the SQT worksheet. The other two worksheets, there's a page that has 10 condition assessments where you can enter monitoring data, and you can see it'll ask you for the calendar year, but also the years post-construction. And then the data summary worksheet will show these outputs where you can kind of track how the project is progressing over time throughout the monitoring period. So you can see here the proposed condition score for this project was a 0.51, achieving 561 functional feet. And over here at monitoring year 5, they achieved the proposed condition score. But you can see that there's a little bit of waffling throughout the monitoring period. From the as-built, it went down a little bit and then back up probably as the riparian vegetation established. So you can see here the riparian vegetation kind of was lowest at the as-built, and then it, improved throughout the monitoring period. Whew. All right, I'll take a breath. I only have a couple slides on the debit calculator for estimating functional loss. So the SQT that I have just presented on does functional change, lift and lost, and you can monitor the condition after construction to validate that proposed condition score. The debit calculator is specifically for compensatory mitigation projects, and I'll go a step further that it really is for third-party mitigation in a case where you're not doing permittee responsible or it's not on the same site. Because if I want to show no debits or no change, I want to show that my project is not going to yield debits, and I'm probably going to use the SQT for that to show that my built condition is not going to impact. So for stream relocation, for example, like I will have the existing condition and then my proposed condition and try to show that those are comparable. So particularly for compensatory mitigation and specifically for third-party mitigation, we created a separate calculator where permitted impacts are usually not monitored. So the debit calculator doesn't have any monitoring. And it can be pretty difficult to validate that proposed condition score, because if you're a restoration practitioner, you're probably much more familiar with pool depths and at least the parameters that are listed in the SQT or provided in the SQT. But if you're really an entity that is focused on flood control or drainage or transportation, you know less about stream functions. So the purposes of the debit tool, number one is, again, that numerical difference between the existing and the proposed condition. Priority number two, or purpose number two, is to link stream impacts to changes in stream functions, not specific activities, because we all know that every culvert isn't created equal. There's a much better way to do a culvert that is nicer to stream functions, and then there's another way to do a culvert that is terrible for stream functions. So we really want to focus on the changes to functions rather than the specific activities. And purpose number three is to provide an equivalency, so parity between your credits and debits. So if you're using the SQT to assess credits, then you need a comparable tool to assess debits. There are 5 worksheets in the debit calculator. I'll tell you this now, there's an option where you can just stop at the debit calculator spreadsheet, so you might not need to use the existing condition or the proposed condition spreadsheet. The project assessment, like the SQT, just requires some basic upfront information. You can put in an aerial photo of your project area. The catchment assessment, instead of informing restoration potential, is more to provide context to where your debits are occurring. So if you're impacting a really good watershed that is likely to have a high functioning stream, then that's something we want to know. Whereas if you're impacting a very urban channel, like the picture Will showed where Charlotte was in the upstream background, it's just important to have context for where these impacts are occurring. And then the debit calculator is highlighted because it is the workhorse. And yes, it is the workhorse of this Excel workbook. I'm going to revisit this slide for a second just to remember that there were 2 outputs of the SQT. So this is how we're assessing change in the SQT, and it is also how we are assessing change in the debit calculator. So you're going to have an existing condition score and a proposed condition score, and that's going to yield a change in condition. And then we're going to apply our unit of measure, so still looking at the stream length, so existing stream length, and then perhaps you make the stream length shorter as part of your impact activity. So that's going to be reflected in your change in functional feet. The debit calculator provides the user with options for how to assess the existing condition and how to assess the proposed condition. There are 2 alternatives for assessing the existing condition and 2 alternatives for assessing the proposed condition, which yields 3 debit options. So the easiest option is going to be debit option 3, where you do not assess the stream. You do not have to assess anything. I mean, complete your catchment assessment so that have a feel for what that stream is functioning like, but you don't have to assess it. You accept a standard score, and you're going to estimate your proposed condition using something I'm going to call an impact severity tier, and I will talk about it a little bit later. The second option for debit options 1 and 2 for assessing the existing condition is going to be to assess the existing condition. So getting out there, getting your boots wet, putting on your waders, and assessing the existing condition. You also have that option for the proposed condition. So the two options for your proposed condition being estimating the proposed condition using an impact severity tier, or actually filling in all the metric field values just like you would in the SQT to assess that proposed condition. So for the existing conditions, there's an option to not assess anything except a standard score. Any stream that is not assessed, we are going to assume it is functioning. It is going to have an existing condition score of 1. If you're out there and you do the cost benefit analysis and say, I know the stream is not functioning and that's a lot of debits I'm looking at, so I'm going to go ahead and assess the existing condition. You can assess just levels 1, 2, 3. You have to assess at least levels 1, 2, 3. You can choose to accept default condition scores for the physicochemical and biology functional categories. So the debit tool differs from the SQT in that it does require assessment. It does automatically score all 5 functional categories, and that is because stream functions are interconnected. And remember, in that Venn diagram at the very beginning, there are a lot of stream functions that we are not specifically capturing in the SQT. So by assessing all 5 functional categories when we're talking about debits, we're just better accounting for parity and better accounting for stream functions. But you can also assess physicochemical and biology, and these default scores will go away and be replaced with your scores for the functional categories based on what you assessed. So those are the 2 options for the existing conditions. For the proposed condition, the easier of the 2 options, so for debit options 2 and 3, is you're going to determine what impact severity tier you are in. So tier 0 is no loss. This reach yields does not require compensatory mitigation. You're using bioengineering practices and there's no loss to the stream. All the way up to tier 5, which is a complete loss. I've paved over it. It's now a parking lot. All stream function is gone, so 100% loss. These tiers are described in the user manual. There is a whole appendix for the user manual that describes in detail different activities and kind of what puts you into different impact severity tiers. So please read your user manual for more information on the impact severity tiers. But again, the focus is on the functions. So if I'm just doing like 50 feet of riprap, that is very different. Or 50 feet of riprap on one bank versus like, let's say, I don't know, 1,000 linear feet of riprap, but it's on both banks and it looks a lot more like channelization. Like both of those activities are riprap, the banks, but they're very different in their impacts to the functions of that stream. So the focus is on the impact to functions when you're selecting your impact severity tiers. All right, my last slide is the harder option, or the other option to assess the proposed condition is to assess it. So using your design documents, you can go in and assess the bank height ratio, riparian vegetation, pool spacing ratio. You can do the physicochemical and biology assessment and estimate how your project is going to impact each one of those metric field values and come up with a proposed condition score and therefore a loss. I think I have a note on here that, you might have to measure these things after the as-built just to show that, you actually did build what you proposed you were going to build. That is the last slide, and I don't have a clock, so I can't tell how I did on time this time.
You are 10 minutes ahead.
Yes. Did I talk way too fast?
No.
I don't think
Okay.
so.
I guess
I
now's the chance if anyone has any questions for Sydney. Also happy to field any questions on how this all may relate to what the Corps may do with this information.
Yeah, this is Steve. Can you hear me? Okay. I'm thinking of this in terms of road construction. Let's say there's a new road, access road, whatever it is, and we're going to put a big culvert in, and let's say it's a fish passage culvert, and the road is, you know, what, 50, 60 feet wide. Would we use this method on here for something that short? I mean, it seems like it would be quite negligible as far as a score. I don't know. What's your thoughts on that?
So I will answer a little bit, but then I'm going to also ask Will to weigh in. So I think actually that is a perfect example of where this tool could be helpful. I think that our ability to quantify the impacts that are occurring due to that culvert placement by using the SQT and the debit calculator will be beneficial both to the applicant and then also to the Corps for determining potential mitigation needs. The more we learn and use this tool to learn about how putting in all these culverts or how doing these projects can impact stream functions, the better I think we can be at working together to find ways to reduce those impacts. Maybe changing how that culvert is installed, or maybe using a bridge instead of a culvert, and looking at our different alternatives for how we can reduce impacts. Does that help answer the question?
Sure.
Okay. Anyone else have any questions? I'm not hearing any. You guys are a very quiet crowd. It's after lunch. I know. Let's get our pump it up again and get awake. I'll take a step outside if you're in Alaska, and that'll be brisk enough to wake you up. But we can continue to move on if there are no more questions. And Will can now kind of give us a tour of the Alaska SQT with a case study. Or Sydney, do you have more to do? Sorry.
I didn't get to it yesterday. If I have time, I can. This is a short one.
Oh, yeah. I'm sorry. I was reading the
thought.
agenda incorrectly.
No, that's okay. I went way over yesterday. So, all right, let me get back to my presenter view on PowerPoint so that I can actually change the slides. So this next part is kind of a tour of your manuals. I tried to reference them in the previous presentation because the answer to many of your questions is probably in the documents that accompany the workbooks. And I have all the workbooks and manuals open that we can take a look at, but I'll work my way through this short PowerPoint first. So the Alaska SQT comes with a user manual, and I've listed out the appendices. Let me get my laser pointer back. So the user manual contains background information. So the presentation Will gave this morning on the stream functions pyramid framework, it includes all the directions on how to collect the data and enter it into the SQT. We have a chapter specifically for mitigation projects. And then this slide is about the appendices, just making sure you know where information is located. So specifically, field data collection is in Appendix A for that user manual. There are some optional field forms. As a practitioner, I usually like to develop my own field forms after performing the assessments in the field. So these are not required field forms. They are optional, provided for your convenience. They are not locked. Feel free to grab them, adapt them how you see fit. Appendix C is that appendix that you're going to need for the impact severity tiers descriptions. So there are example activities and how those were thought about in assigning them to impact severity tiers and how that relates to the functional loss of each of those impact severity tier categories. Appendix D is for macroinvertebrates. So it's a recommended list of macroinvertebrate taxonomy laboratories in case you are collecting that sample where you need to send it. I think only one of them is actually in Alaska, which I found interesting, but we provided you a list of labs that can process that sample for you. You also have this big, wonderful document. So if you are super excited about the reference curves that I showed in the presentation, all of our logic, all of our reasoning is outlined in this scientific support document. So Appendix A is that list of metrics where it has for every metric, it lists the stratification and then the threshold values that we assigned to develop the reference curves. And then it also lists and outlines the development team that, provided assistance in determining those reference curves for developing the SQT. There's a guide to the user manual. This is I think it's figure 1 in your user manual, or at least like up there in it, that tells you what section to go to. So like, for example, if you are looking for instructions, you just want to know how to calculate a specific field value, you're going to go to chapter 2 and find the metric that you are looking for and read the instructions for how to collect that data and how to analyze that data to get that particular field value. Chapter 3 outlines the whole restoration potential process that I had, the 5 steps that end that last bubble of restoration potential, and talks about goals and objectives. And then if you're looking for field data methods and some forms, again, you're going to go to appendices A and B. Appendix A, just to talk about that one a little bit more in depth. Since the SQT is really a collection of assessment methods that are already in existence, you'll see that we don't actually provide all of the instructions. So instead of duplicating information that is provided somewhere else, so if you're going to do large woody debris, percent fines, everybody's going to do vegetative complexity, and some projects are going to do native cover. We're actually going to refer you to the BLM AIM instruction manual for how to collect that data, because those methods are from that assessment method. If you're going to do B-High, oh my gosh, we could not write the manual on that. There are lots of resources available. We do have a point to the River Stability Field Guide from Brosgin, but also this free, and I think there's a link to it in the manual. We can provide it to you if you need it, send you the PDF, but there is an appendix to a STAR et al. Report from 2015 that provides a lot more information on B-High, near bank stress assessment method. And then for physicochemical and biology, similarly, like, we're not going to tell you how to collect a diatom sampling method. That is already written in another document. And there are references in the user manual that tell you, like, follow these methods outlined in this document. The user manual Appendix A also includes an equipment list, an order of operations for the field. It'll help you with bed feature identification, because that can vary so much between different programs and different specialties. We just wanted to make sure we are clear about what the SQT counts as different bed features. So what are pools and what are riffles? We also outlined some rapid survey methods. So rather than taking out a total station or doing a full survey, you can go out and do rapid methods with an eye level and a rod. The order of operations for fieldwork, I wrote this up so that you had it kind of in the slide deck, but we kind of outlined just, start to finish, if you're going out in the field and assessing all 5 functional categories in a field day. I do not recommend that. It would be a very long field day, but if you're going to do that, then kind of the order of operations that you would want to follow, so that if you are going out in the field, you kind of have a place to start of, what am I going to do first? And that is laid out in that user manual Appendix A. The forms that we provide, again, they are optional. You can edit them as you need, but they're a good starting point if you just don't know where to start. There's a project reach form, a rapid survey form, large wood, lateral migration, substrate, veg, and a non-native veg form provided in Appendix B. This is the list of example activities for determining impact severity tiers. So along the lines of, not all culverts are created equal, not all stream crossings are created equal. So if you have a full span bridge, that's a lower impact severity tier than if you have, let's see, culverts that substantially alter channel characteristics. That one's a much higher impact severity tier. And then I think I'll end on this slide, but it's, just the cover page for that scientific support document. And again, there is an appendix to this that lists all of the thresholds used for reference curves and all the stratifications that are used in the SQT. And again, in the SQT workbook, all the reference curves are visible to you as the user, so you can see how it's doing its calculations and scoring your stream. That is Oh, how can I exit? Any questions on the manuals? That was a lot less information than my first presentation, so.
So hopefully the chat's working. There were some questions about where to get things, and I put links in the chat. So hopefully folks saw that. Matt, did you see it?
Yes.
Okay.
I think that's working.
All right.
We're ready for the case study, I think.
Cool. All right, so it's playtime. So before we play, I wanted you to have a mental picture of the site. So the primary objective of this very short PowerPoint is just to show you some pictures of the site. And then I have two announcements that I wanted to share as well. One is just some upcoming training opportunities for people who might be interested, and an update, well, an announcement, I guess, related to a stream design manual. All right, so our case study is going to be just north of Fairbanks. It is called Gilmore Creek. It's at the NOAA facility, if you all are familiar with that. And you can see this red line is the catchment boundary, and then the blue line is the stream reach. You can see there's an active mine in the headwaters of the watershed, but then most of the watershed is forested and vegetated. And then maybe most important from this slide, you can see that our drainage area for the overall project reach is about 5.9 square miles. And then here's a little pin that was dropped right where our assessment reach is. That pin is, you can see it's kind of a light brown area. That is a place that's basically all mine tailings. Here, I'll use my little laser pointer. So these are all tailings. And they basically push those tailings right up next to the stream. So here's the stream reach that we assessed. This was assessed as part of an SQT field day with agencies last summer. And then this is a big hill slope. So it's a very well vegetated slope, but it is a hill slope. So this was all valley, kind of a confined alluvial valley before mining, maybe an unconfined alluvial valley, really. And then it's mostly been filled by tailings. And then you can see some of the mining ponds upstream and a few ponds downstream. All right, so here's some couple of pictures from in the channel. Here's that hill slope, very well vegetated hill slope, pretty small stream. Here's a little mid-channel bar. And then here are the tailings that have been pushed right up next to the stream. So hopefully you're already thinking about the lack of floodplain connectivity. Not much bed form diversity here. There's some erosion. There's some vegetation. Yes, this is from placer mining. And then here's another shot, kind of same spot, but looking downstream. You can see that little island, so on. So that's it. You can kind of keep that mental picture of the stream in your head when we start entering numbers. And then again, just really just a FYI, if you are interested in more in-depth training on the stream functions pyramid and the quantification tool generically, there is an online workshop January 25th through 28th. So that's a Tuesday through Friday. It'll be a little early for most of you. I think most of you are in Alaska. Some of you are in the Pacific Northwest. It'll be most days from 9:30 Eastern until about 5:30 p.m. Eastern. There is also an in-person class scheduled for next year, and that will be at NCTC, is the National Conservation Training Center. It's owned and operated by the Fish and Wildlife Service in Shepherdtown, West Virginia, which is about an hour west of Washington, D.C., in the Appalachian Mountains. It's actually a very pretty setting. It's known as Club Fed. It's like a little college campus that's been plopped down in the Appalachian Mountains. Very nice. And that'll be September 26th through the 30th. And then for people who take that class but want more field experience, there are 2 what we call SQT field camps. So they are kind of what they sound. They're 5 days long. Almost every day except for one is in the field. And so there will be one in North Carolina in April 11 through 15, and then one in Colorado in September the 12th through the 16th. So the only 2 that are open for registration at the moment are the online course and the North Carolina field camp. I would not recommend that you all take the North Carolina field camp. The online course would be fine, but the Colorado field camp would be more like the type of work you would do in Alaska than the North Carolina one, unless you just want to come to North Carolina. All right, and then I did want to let you know about a design manual. So we've been working on a stream reclamation and restoration design manual for a while now, well over a year. The focus is on placer mine reclamation, but we did, I guess about 6 months ago, we were very focused on that, and then the Fish and Wildlife Service got involved and provided some funding. And so with that, we have broadened the manual a bit to make it more applicable to other types of projects like mitigation. It will still be focused on the interior of Alaska. It is pulling a lot of lessons learned from our demonstration projects, which I haven't talked much about, but we've built, I don't know, four to six demonstration projects, reclamation demonstration projects through BLM. We've had success, we've had failure, and so we're trying to bring all of that together to lessons learned and guidance to put in this manual. We are it's funded by BLM with support from Fish and Wildlife Service, and then also administrative support from the Salcho Delta Soil and Water Conservation District. And we are almost done. I expect that we will finish writing in January, and then it will go through a review, edit, publishing phase. I don't know how long that'll take. I really am hopeful it'll be the first quarter of 22, but I gave myself a little bit of wiggle room and call it the first half of 22. By field season, let's say, hopefully it'll be done. All right, so that was kind of our quick little tour. So now we're going to crack open the spreadsheet. This is the SQT, and I am on the first tab. First worksheet is called that project assessment worksheet, and you've seen some of this already from Sydney, but now we're just looking right in the SQT itself. You'll see places on that project assessment sheet where you can put your programmatic goal. So for example, you could list that it's for compensation, so mitigation, credits, debits, non-mitigation. You can just select that. You can enter in, you can do other, and then provide a description. There's a place for you to put the project name. So ours is Gilmore Creek, and it will be Reach 1. And you really do need to fill this out because this gets transferred to the quantification tool sheet. And then the other thing that you have to do on this project assessment sheet, or your quantification tool sheet will return errors to you, is pick the reference stream type. And we did not go into detail with that today. It is in the reference user manual, but it's basically what stream type should be there given the valley type that is there. Not the existing stream type, but what stream type should be there given the valley type before it was messed with. And so in this example, since it would be an alluvial valley before those tailings, the reference stream type would be a C. So you do have to answer that question on this project assessment sheet. The next sheet we're just not going to do today due to time, but this is that catchment assessment form that Sydney and I both talked about. This is part of the restoration potential process. So you would go through here and answer questions about your watershed, and then you could give it an overall, just qualitative watershed condition based on these responses. This is really a decision support tool more so than a a watershed assessment that you might use for other purposes. I'm going to go ahead and say partial here, mainly because there's that big mine upstream. This next tab is that metric selection. So you've seen all of this just in different forms. So here's the categories, the parameters, the metrics, and then just some guidance for you as you're getting into the tool and trying to make decisions on what parameters and metrics do I select for this project. This is a bit of a cheat sheet for you to come and make those determinations. So the next worksheet is the quantification tool. This is where the magic happens. You will spend most of your time on this page, at least until you get into the monitoring phase, and then you'll move to the monitoring portion of the worksheet. So as Sydney pointed out, one of the first things you have to do is fill out this site information and reference selection table. So we're going to do that first. So our stream length was 400 feet. That was the existing. The proposed comes as part of the design phase. I'm going to go ahead and put 400 feet back in because I know that with the most likely restoration approach for this site, you would not increase stream length. Our existing stream type is an F, and so we'll select that. The other thing I'll point out is these gray cells you can type in, and so obviously do that. For these blue cells, they are drop-down menus, and use the drop-downs because some of these items are stratifiers and you don't want to type the wrong word. You want it to be pulling exactly the word from here because it's telling the spreadsheet which curve to use. So when there's a drop-down, use it. And you can see that C was pulled from the project assessment sheet, as was the Gilmore Creek, the reach ID, and then the restoration potential was pulled from the catchment assessment. The valley type, we put as an unconfined alluvial valley. You could debate a little bit on whether it was unconfined or confined. I think based on our measurements out there, it was unconfined. The drainage was 5.9 square miles, so we'll enter that in. The stream order was a second order stream. The flow, and see, as soon as I did that, it put the 2 over here in the mitigation summary and that proposed functional foot minus existing functional foot. And when I pick the flow type, it'll add that too. So now we know we're working in a perennial second order stream. The bed material is gravel. The slope is 0.7%. The ecoregion is interior forested lowlands and uplands. That is a stratifier. It is a non-anadromous fish assemblage, and it is forested vegetation cover. Some of these, like fish assemblage, you do not need if you're only going through geomorphology, which is what we're going to do today. We're only going to focus on those required parameters plus one more that, the bed material will add, even though we didn't talk about that one. But we're not going into physical, chemical, and biology, so we don't have to do this one. But my suggestion is that you just complete this table in full, because if you miss something and then you enter a field value and your index value says false, you're going to want to call Sydney or me, and you really don't have to. Like, it's most likely because you didn't completely fill out this table. So just completely fill it out every time, and you'll minimize your chances of getting a false result. All right, so once we do that, we're ready to enter the existing condition information. So we scroll down, and here's our table. And I'm just going to scroll down. I got an answer sheet here from when we went to the field, so I'm prepping myself here. So we did not do the catchment hydrology parameter. Remember, that is an optional parameter, but we did do the reach runoff parameter because it is required. And we chose to do the land use coefficient and the concentrated flow points. So the land use coefficient was a desktop exercise. That was 11.36. And that's pretty darn good. So our lateral drainage area was not perfect because of the tailings, but there was so much hill slope that was well vegetated. It's a pretty darn good score. Not much functional lift to be had from reach runoff. However, there were 5 concentrated flow points coming down through the tailing piles. So we had a lot of concentrated flow points. That gave us a 0 for the index value and brought our reach runoff parameter down to middle of the road, well, yeah, kind of middle to lower end of functioning at risk. All right, so now we're to floodplain connectivity. And again, hopefully just from those pictures, visually, qualitatively, you could say there was no floodplain connectivity, and there was not, but we did measure it. So our bank height ratio was a whopping 10.7. That is a huge number, and that would give us a 0. And remember, when you get bank height ratios above 2, now your entrenchment ratio is going to start coming down. So we have a high bank height ratio and a low entrenchment ratio. So we have no floodplain connectivity, 0. Then we have that width to depth ratio state, and that can, remember, 100% is pristine. We were a little wide, so it was 110, but still not too bad. That gave us a 0.88, so kind of middle of the road functioning, but not perfect. We did assess wood, and we had a little bit of wood. We had 2.46 pieces per 100 meters. That put us at the lower end of functioning. I will let you guys know, I don't know if you care or not, but you do not have a lot of wood naturally in the interior. So this score that's functioning for you in the Alaska interior would be not functioning in just about every other SQT we've done. I think I can safely say, yes, every other SQT, this would be not functioning. But this is why we regionalize. We don't want to bring Wyoming's large woody debris frequency to Alaska and impose it on you. So it is what it is. But that will not be a very hard score to get into the functioning range for Alaska. All right, so now we're to lateral migration, our dominant behind near bank stress. This is the only metric that's a drop down. So it converts a categorical rating into an index score. So this one was very high. So I'll just scroll down, very high, low. And then our percent stream bank erosion was 47%. And so this is functioning at risk, but just barely. Remember, to get into functioning at risk is a 0.3. So we're at a 0.35, almost at not functioning. There was not armoring, and so we did not assess armoring. We did do the bed material characterization, so that's not something we've talked a lot about today, but we did measure it as percent fines. Mainly because this was a workshop and we wanted to give people the experience to do it, but I'll go ahead and enter it here since we have the data. And now we're into bed form diversity. So this stream had been channelized. It had been moved up next to the hill slope and straightened. So there were no pools at all in our study reach. By rule with the SQT, if your stream is channelized and there are no pools, you would enter a 0. And that's important because remember, Sydney said, if you do not assess a metric, it's just removed from the tool. In this case, we are assessing it. There's just nothing there to measure. But there should be pools there to measure. And so it gets a 0. Same with pool depth, although frankly, at this point, it kind of doesn't matter because the whole thing is going to equal a 0 because you have 100% riffle, no pools, and so your bed form diversity is a 0. So now I won't get ahead of myself. So next is riparian extent. So that whole, basically your riparian area is mostly to the right. There's just a little bit on the left. And so that would be a 0 because it was all tailings and it was not very complex. And then we can leave the native cover blank because you would only do that one if there were non-native species present. And so we'll just assess the riparian extent and the vegetative complexity, and we see that our riparian vegetation is not functioning either. So now when we scroll up, we have some scores. And for me as a practitioner, this table is one of my favorite outputs of the SQT because I can see by parameter what's broken and what's working and what's in between. And so as I look at this, I say, okay, reach runoff isn't great. It's middle of the road functioning at risk. But if I take a deeper dive, I see that, okay, but I really can't do much with land use coefficient, but is there something I can do here with these concentrated flow points? Like that's really bad. And then floodplain connectivity, there is no floodplain connectivity. And it's really one of the things we would always look at as a restoration provider is if there's no floodplain connectivity, how do I give the floodplain back to the river? It's really the place that I would start as a practitioner. Flow dynamics are not bad, so I really don't have to address the width-depth ratio. Large woody debris, like I said, it doesn't take much to get wood into that system. We could improve that score a little bit if we wanted to, but that's really not a place we need to focus. Lateral migration needs to be addressed. Bed material could potentially be addressed if we can remove the tailings as a source of sediment. Got to address bed form diversity, got to address riparian veg. One thing I want to mention here, I can't, Sydney may have mentioned this and I might have missed it, but one thing that we recommend to the Corps and EPA and the IRT from a policy perspective is that they not let practitioners cherry pick. And so you might come here and say, okay, I've got all these things that are wrong, but the cheapest thing for me to fix would be riparian veg. So I'm just going to come to this site and plant a bunch of trees and get my lift with the veg and leave everything else broken. And we have recommended that not be allowed, that we handle that by rule. And we call them the big four. So the big four parameters are floodplain connectivity, bed form diversity, riparian vegetation, and lateral migration. And we recommend that if you're going to do a stream restoration project, you should get all four of those parameters. Well, I'm going to say three. You should get floodplain connectivity, bed form diversity, and lateral migration into functioning, even if it's low level functioning, and your riparian vegetation into functioning at risk. To say that more broadly, without maybe pigeonholing people, you should address and try to fix those four parameters if you're going to do a restoration project. Otherwise, this tool could be gamed, especially in mitigation. You would not want that to happen where people just come in and plant trees because those trees are not going to last. You plant them way up on this terrace and it continues to erode. So just wanted to point that out. Okay, so with this in mind, let me scroll up here. We can also see some scores starting to get populated. So our existing condition score is 0.25. Our condition score delta is minus 0.25. Actually, ignore that because we just have a proposed condition score now of 0. So we've got to populate that. Then we'll get this delta. So really the only two scores that are meaningful at the moment are this existing condition score of 0.25 and our existing functional foot score of 100. So you can see that's just the 0.25 times the 400. So out of this 400 foot long reach, we have what we call 100 functional feet. All right, so let's play. We're going to come down to the proposed condition. And we need to make sure we answer all of the same, we enter data for all of the same metrics. And so we're going to say that for this land, we're not going to even try to change this land use coefficient. Like that's already very good. We will improve it a little bit if we address those tailings, but maybe not enough to even move the needle. So I'm just going to leave it alone. Oops, sorry, put that in the wrong place. Scroll down, 11.36. In the land use coefficient. If I had left that, if I had screwed up and left that, I could have caught that error. When I come up and I look at my parameters, because your parameter score should be the same. And if I did that, suddenly I have a parameter score in catchment hydrology for proposed, but not existing. And that would tell me like, oops, I made a mistake. All right, so we're going to get rid of those concentrated flow points. So what I'm about to do, I'm just going to make up numbers, but I'm going to kind of talk you through a conceptual design. And that really is what the proposed condition is. It's part of your design process. You've done your assessment, you've got your mapping, you're looking at your data, and you're saying, what can we do at this site to fix these problems, and how will that change the score? And remember, the proposed condition score is really more than an as-built score. It's what do you think that score will be at the end of monitoring? And so we're going to get rid of a portion of those tailings and give at least a bankful bench back to the stream. And we're going to take these concentrated flow points and route that, regrade the tailings so we don't have a lot of overland flow to the stream, that some of that can go to some of those ponds that are in the valley. So in doing that, we can change our concentrated flow points from a 5 to a 0. And now our overall reach runoff parameter is well into the functioning range. So for floodplain connectivity, what we're going to do is just build a bench. Now the left side is a hill slope that's totally forested. So we would leave that alone and come on the right side of the stream and create a bankful bench and then slope those tailings up to something that we could stabilize. So we're going to convert that crazy high bank height ratio from a 10 to a 1. And we're going to have a moderate entrenchment ratio, something of about 2.1, because we think that that's kind of feasible. I'm imposing a bit of a constraint here, saying that the landowner wouldn't let us take all of that tailings, because what are we going to do with it? So we're going to take a portion to get a bench and make an observation hill up on top of the high terrace. Now, because this should be a C stream type, but we can't take it all the way back to a C, we're going to use a moderate entrenchment ratio, and that's why it's only given us a 0.4. The bigger we can make that bench, the better this score will be. So if we could go to a 2.5, that would jump us up to the low end of functioning, and maybe that would be worth doing. Frankly, it probably would, but I just wanted to show you that process, so I'm going to put it back. All right, flow dynamics. We didn't have a lot of room to change, but we'll go ahead and get that to be our observed width to depth ratio to equal our expected width to depth ratio. Large wood, we can add a little bit more wood. That wouldn't be too hard to do. Maybe what we do is incorporate some of that large wood into some toe protection as we rebuild that bank on the right. And in reducing the height of those tailing piles and building that bankful bench, creating some toe wood, using some transplants on that bankful bench, we can improve that dominant B high to a low high. Or we could do low moderate. It would give us the same answer. So pick whichever one you want. Once you get into a low B high, it kind of doesn't matter what your near bank stress is. And we'll reduce our percent erosion down to 5. We're going to acknowledge that, hey, there is a little bit. We're not going to add any armoring. We did not have armoring in the existing condition. We're not going to do it in the proposed condition. We are going to assume that we can coarsen the bed a bit. And so we'll bump that down to 10. And then we're going to use some, so if we're going to keep it straight and we're going to do a bench, but we want to have some pools, we got to have a pool forming process. So maybe we're going to put some constructed riffle step pools into this stream. There's usually plenty of rock on a mine site to use, so we could do that. And then we can get maybe a pool spacing of 4. Maybe we don't go too crazy with the pool depth because we recognize that, hey, there is a mine upstream. Maybe there will be enough fines coming down that we can't maintain that pool depth, or there's just so much gravel bed material moving that we're just not sure with a straight channel constructed riffle step that we can get super deep pools. We have actually seen this in the demonstration projects that it can be difficult to maintain really deep pools and systems with high bed load. And then our percent riffle, we can reduce that to 60%. So now we're into the functioning range for bed form diversity as well. Riparian extent, so I said that we couldn't have the whole valley width, but we can have maybe 60%. So we'll put that in there. We're going to improve the complexity a little bit, but we're not monitoring for all that long. And so we've got this 0.5 functioning at risk for riparian veg, but if the average mitigation monitoring time is about 5 years. So this is probably reasonable to think for a 5-year period if we incorporate transplants as well. So now when we scroll up, first thing I'll do is check to make sure I have answers for the same parameters, and we do. And I can just visually see that, hey, we did pretty well with that design. We took everything to green except for riparian vegetation. Some of these are on the low end. Our floodplain connectivity is just barely functioning, but that's huge lift. We went from 0 to 0.7. And same with bed form diversity, from 0 to 0.86. And, pretty good lift for riparian veg. So now we scroll up and we have all of the calculations are done now. We have an existing condition score of 0.25, a proposed condition score of 0.52. So this is a functional lift measure as well. It's kind of your quality measure. And then you add you multiply those values by your links. So we have 100 functional feet of existing stream, 208 for our proposed, and so that delta is 108, and it is a second order perennial stream. And so how much better would our restored stream be than our impacted stream? It would be 108 functional feet better. All right, so I'm gonna stop, see if there are any questions. Or if there's something you want me to play with, I can jam a number in. All right, well, we can move into, if there, we did have sort of the last part of this open to Q&A. So we'll see if you have any more. I did get an email during break that had a few questions. I think I have answered most of them. One was, will the slides from the presentation be made available? Yes, we will do that. No, I do not have any sketches of this scenario. I just totally just made it up on the fly. The user manuals, we answered that in the chat. You can get it from Stream Mechanics webpage or the Ribbits webpage. Sydney, I did notice that I have not put the science support document on the Stream Mechanics webpage for Alaska, so shame on me, and I need to do that. We got the name of the book. So the last question I don't think I've addressed is, it says, can we obtain CE credits or a certificate of attendance for the training? The latter, yes. If you need a certificate of completion, if you will email that request to me, I will email one back to you. All right. So, Ellen, do you have any more comments from the core, or is it just open session?
I don't really have any comments for the core. I would just again encourage you to get onto the Ribbit site, download the procedures document, and that performs sort of or provides a framework for the way the core is going to consider the use of both the SQT and the information received, and including from the debit calculator. So if anyone has any questions about that, now is a great time to ask.
Well, okay, this is Steve. Will, through the scenario you just described, the lift you did on Gilmore Creek. Okay, I'm not really a stream guy, but I am looking for mitigation credits. So when you said that in the existing condition there was no floodplain, and yet it looked like that Placer Valley you showed us, it kind of looked like it had floodplain. So is that because the stream is so entrenched that nothing was really flowing out, right?
That's correct. It's
Okay,
because
so
it was so
under that
deep.
scenario, then we've got to excavate benches from the one side. So we're digging down to create the bench, and we're going to kind of tier that out in some stable pattern.
That is correct.
Okay.
Let me, while you guys are talking, I'm going to bring up a picture from another presentation to just kind of give you would not look exactly like this, but it will give you a flavor.
Okay. So Will, is this a good point to mention that the design manual will talk about some of these techniques, and and I don't know if it has scenarios, but it certainly addresses the various techniques.
Yes, yeah, and it's a stepwise design manual, and I mean it's not. I don't want to oversell it. Like, this is not a design manual for someone who's a wetland scientist and has never done, a stream assessment or restoration to pull off the shelf and go do design work. But it is a stepwise design manual, and it does. We are going to put one of the demonstration projects as a case study in the back. And then we are working, BLM is working to develop a web page to kind of house all of their demonstration projects so that people can start to see that.
Right. And I also will point out, I'll let you keep going. I don't want to distract you, but it is possible for agencies to provide training on the SQT in Alaska potentially, or on design work, right? We've done the stream functional pyramid training and restoration design in the past. So if there's an interest in having training in Alaska on application of the SQT or restoration design, that would be feedback that we're very interested in receiving. So Sydney on her last presentation had a slide that indicated this here's the site that you provide your feedback on, and that certainly would be a valuable input if you're saying, hey, we want to learn how to do this, help us out. Back to you, Will.
Can you, I'm not in presentation mode. I wasn't going to go in presentation mode, but can you see my cursor okay now?
Yes.
Okay. All right. So just first of all, pretend that this side is not bare ground, that it looks like this, because that's more like what Gilmore Creek was, right? The left side was fully vegetated. So just sort of ignore that and pretend like this side is perfect. This side had tailing piles, which is what this is as well. And so just imagine that you create that bankful bench, because you are absolutely right. The reason it did not have floodplain connectivity is because that terrace was those piles were huge. There's really no storm event, no amount of ice blockage that would get water that high. Like, it was massive. If it is, we have huge problems. So what we want is to make sure that that floodplain starts at what we call that bank full depth. And so that's exactly what has been done here. This is the bench. So you would cut a bench into those tailings, find transplants nearby, willows, alders with some herbaceous mat is great, and put those transplants on that bench. And then here's the back of the bench, and then slope that up, and then this all gets vegetated. So this is more of that where the reach runoff parameter could get scored a little bit better, but this is where your riparian veg is going to get scored. And then if you look inside this channel, like this has all been rebuilt. This is that constructed cascade with a step, and you can see a little bit of white water that's coming into the pool. So you have a cascade, step, pool, riffle, step, pool, and you just keep doing that all the way down. So that would be the same technique that you could use here. This is a bigger system than Gilmore, like twice the size, I think. If that was, I think, maybe not. Maybe this is closer to 8 square miles. It is bigger. Matt?
Yeah, so this is what you're showing. This is White Creek, and I believe BLM, this is one of BLM's demonstration projects. I believe they made some recordings, some video actually during the progress of this work. I think their intention is to actually make that available. So, or maybe they're doing a report on multiple of these demonstration projects. So as Will said, BLM in particular has been compiling data on what has been successful in terms of techniques and methods, and what methods have not been successful. And they're going to be, they're doing a lot to make that information available to folks.
We might could just do, I mean, it would be logistically a little bit challenging, but maybe a demonstration tour would be a good thing to do at some point. Just take people out and show them the successes, show them the failures, what we've learned, and that'd be something to think about too. That would, this is along the Alaska Highway. The other demonstration projects are past Chicken and the Jack Wade Creek, so these are not near each other, but it's Alaska.
Right. So just one other thing on the Gilmore Creek case study, could you speak to how or if the ponds that are in the valley are being captured or affected by your proposed condition? Or maybe they're not.
They really are not. Other than the fact that I saw it as an opportunity to run some of that overland flow into those ponds instead of right over our, freshly graded slopes, but that's about it. Now, some of those upstream could actually help. You know how I was sort of shortchanging the pool depth a little bit? Those ponds up there could actually help our pool depths a little bit. So, if I was a practitioner and I was uncertain and I was doing this for mitigation, I would tend to sandbag my proposed condition in hopes that I would do that or better. But I will tell you that the trend is the other way. People will often be like, I want 1.0s for every single metric. And you can put that in the SQT. It will allow you to do that, but you will not achieve it. And so what happens through monitoring, and if you had a credit release schedule, you would not get as much credit as you predicted you would get in the proposed condition. So I like to be, I would rather under promise and over deliver than the other way around.
Right. And it's just the image, the photos you showed may be a little bit deceptive because the ponds are not connected to the existing channel, current channel. They're up on the terrace on top of the tailings. Is that correct?
So they do connect farther downstream.
Yeah.
When you get downstream, there's like an old, I don't know if the whole thing was a pond, but then it's not incised at all. In fact, you might even argue that Bankful is not even the top of Bank. It looks like the whole valley was sort of a pond, and now it's just sort of a grading. So it's a very different system when you get a little bit farther downstream.
Okay.
Okay.
I see
Any
some
other-
thumbs up for field training in Alaska. Yes, I hear you. I made my first trip to Alaska in 2012, and I have been every year since, usually multiple times, doing a whole variety of research, except for 2020 for obvious reasons. So I hear you. Field work in Alaska rocks.
Any other questions? I can't see the chat, so someone will have to advise me if there's anything in the chat. And then I would also like to say that, you know, I've been involved in this project and forming the SQT as much as I could for a while. And I am absolutely happy to talk to anyone who may propose using this tool. And I would ask someone on the team here to put in my email, ellen.h.lyons@usace.army.mil, as well as a phone number. My new work phone number is 907-347-3481. For those of you who have worked with our office before, we have moved on to Fort Wainwright. And so you need to call ahead in order to get on, but we're happy to help facilitate that. But, you know, you can call and chat with me about the use of the tool or kind of what you're thinking, how to incorporate it into your proposed project, should you desire to do that. And as I said at the beginning, you know, we're not going to require the use of this tool. That isn't how the Corps operates, but we really do encourage its use. We think this is a very valuable tool. We have helped in the, you know, putting it together. And I really encourage you guys to look for opportunities to use it, because the more you use it, the more information that we have to make good permitting decisions for everyone. And that's really all I got, unless anyone else has anything.
There was a question that just came through. It says, I noticed permafrost degradation and off ice in the catchment assessment. Do those just feed into the overall watershed condition and restoration potential? Yes, they do. They're used as part of that decision support tool on what you're kind of can flow into the design process, but it's not something we're measuring in the SQT. That was a pretty good catch to see that quickly when we were on that spreadsheet. That was a good eye.
Yeah. Well, yesterday, Will, you talked a little bit about adding metrics or parameters and to the SQT and the real need to have a measurement method to do that, and then be able to get reference data or you know, data from the literature to create a curve in order to score it. So as Sydney pointed out, there's lots of potential metrics. There's lots of potential functions that are not part of the SQT. In many cases, that's because we don't have good measurement methods. And so, you know, a lot of stream work and assessment methodologies have been developed in the lower 48, and they don't really worry about permafrost degradation down there or off ice processes. So there's, you know, standard assessments that may have been developed somewhere else would not have those metrics. So if there are folks in Alaska with expertise on permafrost processes or off ice, if there's a metric you're familiar with, by all means, point out and say, hey, this is important for these types of streams in this part of the interior, and we think you can add it, make that suggestion.
All right. Sounds like a wrap.
All right. Well, I just want to say thank you to all of you who have attended this. I'm really glad that we're seeing such great interest in this tool. I think it's going to be a real benefit for work in the interior of Alaska. I also want to really thank Matt and Will and Sydney for helping put on these trainings. And if you have any further training requests or ideas, do reach out to us and we'll see what we can set up. But I really, again, appreciate everybody's time and effort on this. So thank you very much.
Yeah, thank you, Ellen. Thank you all. Have a good rest of the week.
Bye.
All right.
Bye.
Watch for the email with the video links to the recordings and the presentations.
Thanks.